So, in the last lecture, we saw how the shear flow creates instabilities in waves, right? And those waves or those instabilities are very common in nature. As you can see in these images, where we have some clouds which are in form of wave, but they are unstable waves, right? And there is wave breaking, overturning of wave, and that actually eventually leads into this mixed wave, right? And that is why you also see that in some cases there is a kind of diffuse wave where you see this part, for instance, is looks much more mild compared to what you see at the top. That means, or this is much more diffuse compared to what you see at the top, right? So there is mixing happening between the cloud and the ambient air. uh, so this mixing that you see here is happening because of a shear flow. And once again, what is the shear flow? There is a velocity gradient in the transverse direction. In the vertical direction, if your primary flow is in the horizontal direction, right? And there are many examples, many cases when such kind of shear flow happens, and which actually brings into instability, and that eventually leads into mixing, right? Like exchange of warm and cold air near the seashore, where you have these cold or warm air flowing uh, towards the sea, and cool sea breeze from the sea coming to the left, right? So basically there is now a shear flow where uh, the upper layer is moving to the right, which has different density, let's say that is rho 1, and the lower layer is moving to the left, right, which has density of rho 2. And there is let's say u1, and here it is u2, so there is delta u and also delta rho, right? So there is a shear flow, and there will be a mixing of this warm air and cold air, right? In likewise case, if you think about an internal wave in the ocean, right, these internal waves that we have, that is formed between two different densities of fluid. So this is, let's say this is less salt, and this part has more salt, right? So both are salt water, but one is with less salt, one is with more salt. So there is a stratification of density, so that creates internal waves. And now this internal wave will break, and they will these two layers will mix. So eventually there is a transport of momentum or salt or heat, etc., right? So mixing is an end process of the wave, wave instability. So that is also shown in this simple example here. So you have a buoyant fluid that is going to the right, and dense fluid that is going to the left, right? So this is going to the right and this is to the left, and they have different density. So that is an stratified medium at the moment, right? So this is a stratified medium. But now, because there is wave that is getting created, and there is overturning of wave, that because of the instability, that overturning brings mixing between these two layers, right? And eventually at late time, you will see that a large part of this fluid have got mixed, right? These two layers of the fluid have got mixed, which initially had this sharp interface, right? There was a clear distinction between the upper layer and lower layer, but at late times there is not clear distinction, right? So this stratified layer has now turned into a mixed layer, right? So what's happening is, in case of a stratified layer, where when there are two distinct layers of densities, there is a lot of velocity in the fluid, which velocity might be coming from some other source. So it has higher kinetic energy, it has higher kinetic energy. And now, because of instability plus mixing, this actually leads into higher potential energy. And how it is converting into potential energy? Because now you can see it has got mixed, so there will be denser fluid which has gone above this interface that was there originally, right? So more and more denser fluid have gone up. So denser fluid has gone up, and lighter fluid has come down, right? So that is how you're increasing potential energy of the system, because you're moving more dense fluid against the gravity, right? And likewise the lighter fluid is coming down, so that is also against the gravity, right? And that is how your kinetic energy is converting into potential energy due to this mixing that we have in this particular system, right? So this is very common in nature. Whenever there is shear flow, that kinetic energy that's there in the shear flow, that converts into potential energy due to the mixing that is coming from the instabilities formed in the waves, right? And the details of instabilities we have already seen in the last few lectures. So today we are going to analyze one simple case of mixing in case of a shear flow, right? And that is this particular case we will start with, where we consider we consider two layers of fixed depths. Okay, so obviously there, in most of the cases the depths are not of fixed depth or fixed value. They are they extend to large value both vertically and vertically upward and downward. But here, to make the problem little simplified, we will consider there that these two layers have fixed depth, and here the upper layer is not really easily visible, but we will assume that this is the upper layer, right? And upper layer has, let's say, the velocity u1, density rho1. Okay, upper layer is moving with velocity u1, which has density rho1, and lower layer is moving with velocity u2 and density rho2, where u2 is smaller than u1 and rho2 is greater than rho1. So system is initially stratified with higher density at the bottom, and now there is a shear flow. So what you have here, this basically means that system is it has a shear flow, and this part means that system is stratified, right? But at later time, due to this shear flow, there is a mixing, right? Mixing, and we assume that it, after long time, this layer is completely mixed, and the complete layer has a velocity of uh, a new density of rho, right? Or rather we should call it new velocity and new density, right? Which are basically the velocity and density of the completely mixed layer, right? So once again, what is happening, the initial kinetic energy in the system is converting into potential energy in the system. So basically kinetic energy decreases due to mixing, and potential energy increases due to mixing. And that is why we are going to analyze kinetic energy and potential energy of the system. We will try to find how much kinetic energy was there initially, how much kinetic energy is there after mixing, how much potential energy was there before, and how much after mixing. Okay, and that is why let's try to find kinetic energy and potential energy. But in the meantime, we also need to define these rho and u, which we define as the new velocity or new density. So basically, based on momentum conservation, we define the depth averaged final velocity u to be equal to u1 h1 plus u2 h2 over h1 plus h2. Okay, so this actually means that your momentum is conserved in the system, and that is why your velocity, which can also be, we can actually do it as something like this: u h1 plus h2 must be equal to u1 h1 plus u2 h2, right, where u is the final velocity in the system, and this is for momentum uh, per unit depth and per unit mass. So we are doing it for an average density, which is considered average based on the Boussinesq approximation, and that is why the density term is not there, and that is something we are going to discuss shortly. But velocity here can be defined as u1 h1 plus u2 h2 over h1 plus h2. Okay, which is based on Boussinesq approximation that we have discussed before. If delta rho is a small, then we consider rho 1 to be equal to rho 2 to be equal to rho infinity. So we consider both rho 1 to be equivalent to rho 2, and that can be equal to rho infinity. So we are applying Boussinesq approximation, and whatever we are trying to derive is based on particular that case. Okay, so this is based on momentum conservation. Likewise, based on heat or solute mass conservation, we can define rho, the final value, as h1 plus h2 is equal to rho 1 h1 plus rho 2 h2. Okay, so this is coming based on heat conservation or solute mass conservation, depending on whether the stratification is because of different temperature or different concentration. So this gives us depth average density, that is rho 1 h1 plus rho 2 h2 over h1 plus h2. Okay, so this is the depth average final density of the mixed layer. Okay, whereas the velocity is depth average final velocity of the mixed layer. All right, so we have now defined final velocity and density. So we can now find out the kinetic energy and potential energy of the system before and after the mixing. So let's start by finding kinetic energy. Initial kinetic energy. So we will name it as Ki. And how can we define kinetic energy initial value? So we will go from 0 to h is the total depth, right? And we will define it as rho u square dz. Okay, that is basically like mu square, where density works as m. So this is kinetic energy per unit volume, right? So this will give us per unit area because there is dz integrated. All right, so here we will consider, so 0 to h2, that is rho 2 u2 square dz plus h2 to h1 plus h2 rho 1 u1 square dz. Okay, remember that this value is h2 and this value is h1. So h2 is filled with rho 2 and has velocity u2, whereas h1, the upper layer, is filled with density rho 1 and has velocity u1. And that is why our equation looks like this. But here we will apply Boussinesq approximation, which tells that rho 1 is equal to rho 2 if delta rho is very small, right? And we can do it here because it's not multiplied with the gravity term, right? Because Boussinesq approximation works everywhere else except when it is multiplied with gravity, and that's why here for kinetic energy we are able to do it. And that is why we will define rho 1 equal to rho 2 equal to rho infinity. Okay, we will call rho infinity, that is the reference density. So this will give us rho infinity u2 square h2 plus u1 square h1. Okay, so this is the kinetic energy initial. Okay, that is there before mixing. And I just realized that we are supposed to keep a factor of half here, so that will come. So this is the kinetic energy we will get, right? So that is the initial kinetic energy. And now let's try to find final kinetic energy, which is after mixing. Okay, so we will call it KEF. So here it is much simpler. So this again goes to h, half rho u square dz. But now we know that u is depth average velocity, and rho can simply be considered as rho infinity again. So rho infinity u square dz 0 to h, that gives us half rho infinity u square h. Okay, this is the kinetic energy we get after mixing. But at the same time, u square is something that we have already defined, or u is something that we have defined, that is u1 h1 plus u2 h2 over h1 plus h2. So that's why we can write u square as u1 h1 plus u2 h2 over h1 plus h2. This is squared, and remember that h is h1 plus h2, right? So that is h is h1 plus h2, so that will cancel with one of the terms. So this will give us KA first, rho infinity by 2 u1 h1 plus u2 h2 square over h1 plus h2, right? So that is our kinetic energy final. All right, so we have got both KEI and KEF. So based on this, now we can find the reduction in kinetic energy due to mixing. Okay, so if mixing happens, velocity decreases, right? And that converts into potential energy. So we will call it delta KE, that is KI minus KEF, right? It's very straightforward. So this will give us, let me simply copy this term here, minus rho infinity by 2 u1 h1 plus u2 h2 square over h1 plus h2. All right, so this will eventually give us rho infinity over 2. If we do the complete expansion, we should get this term as u1 square h1 h2 plus u2 square h1 h2 minus 2 u1 u2 h1 h2 over h1 plus h2. All right, so this is what we get after expansion, where some of the terms will get cancelled, and this will further simplify to rho infinity by 2. We can take h1 h2 out, and that gives us u1 square plus u2 square minus 2 u1 u2 over h1 plus h2. So that basically gives us rho infinity over 2 h1 h2 u1 minus u2 square divided by h1 plus h2. Okay, so this is delta Ke, that is change in kinetic energy, right? And similarly, we can also find the change in potential energy. So the potential energy is something that is simply related to rho gh. That is something what we know. Let's define the initial potential energy, that is obviously before mixing. We can call it PI, which will be defined as 0 to h rho g z dz. So that is the total value, but we have to break it down from 0 to h2 to rho 2 g z dz plus h2 to h1 plus h2 rho 1 g z dz, right? And now here we cannot apply Boussinesq approximation. Why? Because g is multiplied. Okay, here Boussinesq approximation is not valid here, right? Because g factor is there, and as we have discussed, whenever G is multiplied with the density, we have to consider the actual density, because that is what defines the potential energy, or that defines the buoyancy force, right? And that is why this equation will become rho 2 G H2 square over 2 plus rho 1 G H1 plus H2 square minus H2 square. This is divided by 2. So this is what we should get before mixing, and that gives us we can expand it, and this will become rho 2 G H2 square over 2 plus rho 1 G by 2 H H1 square plus H2 square plus 2 H1 H2 minus H2 square. So that obviously will cancel this one, and we will eventually get this is rho 2 G H2 square over 2 plus rho 1 G over 2 H1 square plus 2 H1 H2. Okay, this is potential energy initial, right? Which I think is correct. So this is the initial value, and now we can also get final potential energy after mixing, right? So to do that, PF is again integrated from 0 to capital H rho G Z dz, and here the rho is the depth average density that we have already defined, and this will give us rho G H square over 2, where we can write rho as the depth average density that we have defined here, this one. So this can be written as rho 1 H1 plus rho 2 H2 over H1 plus H2, and this is G by 2 times H1 plus H2 square. Alright, and this will give us potential energy final as rho 1 H1 plus rho 2 H2 over H1 plus H2, sorry, that will cancel. So G over 2 H1 plus H2. Okay, so this is the final potential energy we get after mixing. We can now find the change in potential energy, or increase in potential energy basically. So increase in potential energy due to mixing, right? So we will call it delta PE, that will give us PF minus PEI. Okay, so PEF is just right here, so we will copy it. Okay, minus PI is okay, so if we expand all these terms, we should eventually get so this will give us G over 2. This is rho 1 h1 square plus rho 1 h1 h2 plus rho 2 h1 h2 plus rho 2 h2 square minus rho 2 h2 square minus rho 1 h1 square minus 2 rho 1 h1 h2, right? This is the expansion of these terms. Okay, I think that is correct, and that is why uh, this will cancel with this one, this will cancel with that one, and one of the other term will also get cancelled. So delta PE we get is G over 2 rho 2 h1 h2 minus rho 1 h1 h2, or in other words delta PE is G over 2 rho 2 minus rho 1 h1 h2, right, which we can also write as delta rho G over 2 h1 plus h2. So this is the change in potential energy we get, where delta rho is simply rho 2 minus rho 1. Okay, and now we will analyze how this change in potential energy and kinetic energy relate to each other, and in what kind of conditions we get mixing, or what kind of conditions we don't get mixing.